We now look at another counter example that involves D flip-flop. And the question reads, a consequential process has the state diagram illustrated below. Design the circuit using D flip-flops and decoders. So this is a sequential process that may be considered to be that of a counter. And as we have already met this design process before, the first step is to determine the states that we have. And we knew from the state diagrams that the states are represented by zeros or by circles, and therefore we have four states: state 0, 0, 0, 1, 1, 0, and 1, 1. And therefore the next step is to determine the number of flip-flops required, because we know that one state of a sequential process is represented by one flip-flop. And therefore this means that with the four states we can say that 2 to power 2 is equals to 4. 4 is the number of states, and therefore the number of flip-flops required is 2. Having said that, we also notice that we are told to use the D flip-flop. Therefore the next thing would be to remember or to recall the excitation table of D flip-flop, which we know very clearly from our last few lectures that we normally set our excitation table to be defining, if you are moving from the present state to the next state, what is the required input. And in our case for a D flip-flop, the input is D. And therefore, because we know D has two states, has two possible states, we should be able to define the excitation table as follows. We are moving from state 0 to 0, 0 to 1, 1 to 0, and 1 to 1. That is a typical design of an excitation table, and we ask ourselves, what do we require so that a D flip-flop will move from 0 to 0? And we know that this is called a delay flip-flop, and therefore the next state always follows the input to D, and therefore we know that this will be 0, this will be 1, this will be 0, this will be 1. That is always how the excitation table of a D flip-flop looks like. And that is what we have right here. This is exactly what we have developed right here, and therefore I can clear up mine. So this is the excitation table. So once we have known the excitation table, the step 1 was to determine the number of states. Number 2 was to determine the number of flip-flops, and number 3 was to develop the excitation table. Number 4 will be to generate the state table of our sequential circuit or sequential process. And the state table simply asks, how are we transitioning from present state to the next state? And what are the required inputs? So whenever we see some number accompanying the transition arrow, we know that to be our input or external input required. If we see them separated by a stroke and another number, that number represents the output that follows that sequential transition. So we develop our state table, and we know that the state table always has the present state, the next state, with the required inputs. And for this case, we are going to say that our present state is moving to the next state dependent on some number of inputs. So we can say that our present state is represented by two flip-flops, QA and QB, and the next state will similarly be that. But for the first two cases, we are going to consider when X is 0, and for the next two columns, we are going to consider when the external input X is 1. And therefore, these are still QA, QB, QA, and QB, but they are representing the next state. So we are observing from this diagram that we are starting with state 0, 0. We ask ourselves, when the input is 1, we go back to 0, 0. But when it is 0, we go to 1, 0. The next state is 1, 0. And we ask ourselves, when the external input is 0, we go to 1, 1. But when the input is 1, we go to 0, 0. So we are only observing the arrows and determining where we are going when we have a given input. So we are at state 0, 1. When x is 0, we remain there, but when it's 1, we go to 1, 0. And finally, we are at state 1, 1. When the external input is 0, we go to 1, 0. And when the external input is 1, we go to 0, 1. So this is what is called the state table of our sequential process. So our state table now is similar to what we have developed. So this is what we have developed right here. This is what we have developed right here, and apparently we only interchanged when we are considering 0, 1 and 1, 0. But you can see for 1, 1, we are going to 1, 0 and 0, 1. This is just observation and capturing the information that is represented by this state diagram in the state table. So step number 5 that we usually follow when we are designing the sequential process, we normally, once we have developed the state table, we normally develop the excitation table of our sequential process, and this is what we develop next. And the difference between the state table and the excitation table is very simple, that the state table doesn't have the required inputs of the flip-flops, but the excitation table includes those inputs. Therefore, we are going to draw it now. The excitation table of our sequential process will take the following form. We know we have the present states, which we can represent by QA, QB, that is our present state. And we ask ourselves, our external input is our X. And then what is the next state that we have? We have it QA and QB. And the required inputs, can call them required inputs. And we know the required inputs for D flip-flops are going to be DA and DB. Therefore, we just capture the data that we have in our state table here, and we feed it here. The only data that will be missing is the required inputs, which we will get from our excitation table. So I will just fill in this data. From state 0, 0, we go to 0. When x is 0, we go to 1, 0. And from state 0, 0, when x is 1, we go to 0, 0. From state 0, 1, when x is 0, we go to 0, 1. And from 0, 1, when x is 1, we go to 1, 0. So I will fill in the others. So this is our excitation table. The only bit we have not filled in is the required inputs, DA and DB. And we have said that QA will always follow DA and QB will always follow DB from our excitation table, and therefore we know that the values of QA will be equal to the values of DA. So I will just copy that 1, 0, 0, 1, 0, 1, 0, 1, and then for QB we will just follow 0, 0, 1, 0, 1, 1. So this is our excitation table. And now the only thing that we are yet to implement is our combinational logic circuit that we need in order to finalize our sequential design. And there is something that we have an advantage. We are told to implement it using the decoder. And what we know is that the decoder implements min terms. Therefore, because we have arranged these combinations of Q's and X in the numerical order, then we can simply see that they follow the normal labeling of min terms. Therefore, we can call this one to be M0 because it is 0, 0, 0. This one, next one is M1, 1, 0 is M2, 1, 1 is M3, M4, and M7. And therefore, we can simply ask ourselves, D is A is equals to what in terms of min terms? We can simply say that D is going to be given by min term 0, min term 3, min term 5, and min term 7. And DB is going to be given by sum of min terms 2, 4, 7. And therefore that, because that is our design, the only remaining step is to implement our final circuit. And a final circuit is going to be made up of 2 D flip-flops and a decoder that implements these 2 combination of minterms. And therefore, our next diagram shows us that. So as you can see, we have two D flip-flops. They are fed by the same clock, and we have seen DA is sum of minterms 0, 3, 6, and 4. 0, 3, 4, and 6. And for DB, we have seen that it's fed by minterms 2, 4, and 7. And those minterms are always taken through an OR gate, and the OR gate is the one that is fed into our D flip-flop, and therefore the input to our 3 to 8 decoder is simply QA, QB, and because we are arranging them in the order QA, QB, and X. X is our least significant bit, and QA is our most significant bit, and therefore the least significant bit is fed by X, QB gets into 1, and most significant bit is our A, feeds into number 2, and that becomes our decoder with the flip-flops implementation of our state diagram.